Welcome to the Global Composites Experts webinar series. My name is Wenbin Yu, Director of the Composite Design and Manufacturing Hub. This webinar series is to examine the history, present capabilities, and future of composites, with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in this beautiful Indiana Manufacturing Institute. All of you are welcome to visit us when life returns to normal and it is safe for us to travel. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, SciTech Survey, MAC Software, and Modex 3D. We greatly appreciate their financial support for CDM Hub. Next, I will show a brief commercial from one of our sponsors.
In case you are wondering, you are not fighting molding defects alone. Introducing Moldex 3D, your plastic injection solution. With powerful molding simulation features, friendly and easy-to-use interface, Moldex 3D pinpoints design problems before production and achieve better product quality with less time, less cost, and less waste. Moldex 3D, the best partner for plastic industries.
Thanks again for our sponsors' support. We invite more organizations to join them to serve the global composite community together. This webinar will be recorded and made available on CDM Hub. An email will be sent to you once the recorded video is available online. The presentation will last about 40 minutes and will have about 15 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. After the speaker's presentation, your questions will be read and answered. Next, I will ask Dr. Pipes to introduce our distinguished speaker today.
I am delighted to introduce Klaus Friedrich, clearly an expert in composite materials. In the recent Stanford Ranking List 2020, he ranked 85th of 177,931 researchers in the field of materials. His 900 papers have received 28,742 Google Scholar citations. I had the wonderful good fortune to meet Klaus early in his career when he visited at the University of Delaware Center for Composite Materials as a von Humboldt Fellow. His first academic appointment was at the Technical University of Hamburg-Harburg. He then became the founding research director for materials science at the Institute for Composite Materials at the University of Kaiserslautern. Klaus's scholarship has covered a broad range of topics in composite materials that include tribology, friction and wear, fracture, composites manufacture, and more recently, additive manufacturing. Perhaps the most notable experience that I can recount about our long association occurred on a trip to Saudi Arabia, where I was participating in a study of higher education in that country. We visited all the major universities and hospitals where research was being undertaken. While visiting King Saud University, I was directed to see the portraits of the major scholars who were associated with that university. And lo and behold, I saw Klaus's image on the wall in a portrait form. What a delight it was. Klaus was also added significantly to the archival literature in the book form. He authored 2 volumes in the Elsevier series on composite materials, friction and wear of polymer composites, and application of fracture mechanics to composite materials. He's also authored Composites Tribology, multifunctional composite materials for Elsevier, and more recently, additively manufactured composites. What a pleasure it gives me to introduce Dr. Klaus Friedrich.
Well, thank you very much, Byron, for this kind introduction, and also welcome to my presentation today. About 27 years ago, I wrote a similar book called Advances in Composite Tribology, and this appeared in the composite book series which Byron Pipes edited at that time for Elsevier. Today I thought it's time to bring up some new results which we have achieved in the recent years, especially on polymer-based composites. And for this I have a short introduction which shows you that I first give you some principles of testing of low friction and high wear resistant polymer composites. This means composites which mainly run against smooth surfaces and who should have low coefficient of friction and high wear resistance. Later, I will give you some special examples which we have worked on in the recent years. So in my presentation, you first will see that polymer composites are already used in many different applications where tribology is a critical issue, not only in bearings or gears or flat sliding elements or rollers, but also sometimes as very thin coatings on a metal substrate. For example, these hybrid bushings, which I will explain a bit more later, and also these kind of thin layers, which are used on pistons which run in automotive engines, especially in case we start the engine, then the cylinders are not full of oil, so we must have a material which prevents fretting between the 2 aluminum components. The general principle how we design our material will be shown on this slide here, where we say when we want to reach a polymer composite with low friction and high wear resistance, then we at least use certain kind of traditional fillers in the polymer we are using. The polymer itself should, if possible, offer high temperature stability, at the same time easy processable. For example, a thermoplastic material which can injection mold it into very many parts in a relatively short time. But often these higher temperatures have a relatively high surface energy, so we need some internal lubricants in order to reduce the friction coefficient and at the same time also to form a transfer film on the metallic counterpart and to flatten out the asperities on the surface of the counterpart. The third traditional filler are fibers. In most of the cases, short fibers, but in some exceptional cases, We can also use continuous fibers. These short fibers improve the creep resistance of the polymer. They enhance the strength, the stiffness, and at the same time also the wear resistance. In recent time, additional components, often nanoparticles, were added to the system, and they give us other advantages, for example, enhancing the thermal conductivity so that heat is faster moving out of the contact region. Also, we can smoothen the surface topography and at the same time stabilize the transfer film which is built by these internal lubricants. This is a typical microstructure of such a material, in this case only with the traditional fillers. Here we have a high temperature polymer matrix, in this case it's PTFE. Then the shiny particles here, these are graphite flakes, they are internal lubricants, although PTFE is already lubricating itself quite well. Then we have harder PPS fillers that stiffen the matrix, and we have additional fibers, which are all these ellipses and fiber pieces which give the higher creep resistance and strength. The testing of these materials, usually in the laboratory, is carried out by a pin-on-disc configuration. That means the pin, which is our specimen, rotates against a counterpart, which is often a steel disc, and we can adjust the applied load. We can adjust the sliding velocity, also the duration of the test, and also we can beforehand determine the density of our material, because we need this for evaluation of the tribological parameters. The output are the frictional force, the sliding distance. We can measure the depth loss, delta H, the weight loss of the pin, and the weight loss of the steel disc, which is usually much lower than that of the pin. From this we calculate our tribological parameters. Here I have the most important one is the specific wear rate, which is also called the wear factor of the material, which in turn is the volume loss per normal load and sliding distance. But for the engineer, often also the so-called depth wear rate is of interest, which gives us a measure for the reduction in height per time. So this indicates, for example, if a bearing has too much of a clearance, so that it must be replaced before larger failure of the component itself takes place. And this factor, this depth wear rate, can be related to the wear factor and the product of pressure and velocity. In any case, all definition of wear, the reciprocal value is the so-called wear resistance. If we look at this equation a bit more closer and would plot it in a diagram where we have on the y-axis the depth wear rate, on the x-axis the PV product, then usually for a given material, the curve is relatively linear in the beginning. Perhaps some scatter is there due to a little bit different influence of pressure and velocity. But as long as this wear factor is independent of pressure and velocity. But then there comes a point where the curve increases up to infinity at the end. Here, the wear factor is also dependent from the pressure and velocity product. To improve this material, we can go different steps, either using a higher temperature polymer matrix, fiber reinforcement, internal lubricants. These are the traditional fillers. And if we add in addition nanoparticles, for example, we can even more reduce the slope of this curve and enhance the load-bearing capacity at which finally the curves go to infinity. This is an example of such a result for two different matrices. One's the epoxy matrix and one is a polyamide 6,6 matrix. In this case, we have only traditional fillers, PTFE particles as internal lubricant, short carbon fibers. Here only short carbon fibers and graphite. And you see both curves are in this range and this typical linear and then the deviation from linearity. If we go and add additional nano titanium dioxide, then you see that the slopes are much flatter and also the PV value which can be applied is much higher than in the previous case. This will be also shown in a special example. Here we are talking about diesel fuel injection pumps which were used in automotives, for example, from BMW or Mercedes-Benz. And once they complained to the producer of these pumps, which was the Bosch company, that these hybrid bushings, these journal bearings, which were diesel fuel lubricated, failed too early, so that the whole pump had to be built off the car. And these journal bearings, they consist of a steel backing. And if you look at the higher magnification here, then we have the steel substrate on the outside. On top of that, there is a sinter bronze sintered to the steel. And then we added our composite material, which gets linked to the substrate by these open spaces of the sinter bronze. Also the local adherence of the polymer to the surface. And here in this low magnification figure, you can see only the short fibers, mainly oriented, not more or less parallel to the surface of this bushing. And if we go to a higher magnification, just to look at the composite with a closer look here as a fracture surface, you can see that the short carbon fibers are embedded, in this case, in a peak matrix quite well. So the adherence of the polymer to the fibers is very good. That we also have a good dispersion of the graphite flakes at different locations here. And if we blow up a matrix area, for example, in between the fibers, then you see that there are tiny little particles distributed uniformly. And these particles are zinc sulfide nanoparticles and titanium dioxide nanoparticles, which you can also evidence by an EDS spectrum. Here we have the titanium dioxide, the zinc sulfide peak. If we compare this new material, which we have called briefly nano peak, with the PTFE reference, which was the matrix material before, in addition with some other fillers, then we can see that the new material, especially in a higher temperature range, gave us much better behavior in terms of the specific wear rate than the reference material. And in fact, at 225 degrees testing temperature, the wear was reduced by 75%, which refers to a lifetime enhancement of factor 4. Also, the coefficient of friction was improved, as you can see, between the green and the red curve. And at highest temperature, our frictional losses went down by 65%. So that means the heat development in the contact area is also much lower. At this point, I like to refer to some examples which we carried out in the last couple of years. The first one refers to electrically conductive multifunctional polymer bearings. Always then, when different properties are necessary for the function of a component in a bigger structure, for example, electrical conductivity as well as higher environmental temperature, then we must design our material to withstand this kind of loads. So, and in that case, we call it a multifunctional material. In the present case, if we want to make a polymer ball bearing, all the polymeric parts, the ring and the cage and the inner ring, must be electrically conductive, which is for polymers normally not the case. They are insulators. It must be high temperature resistant polymer, and we must control the strength, the modulus, the toughness, as well as optimize the tribological performance. In the present case, we use polyphenolane sulfide, which is a high temperature thermoplastic. And as fillers, we use multi-wall carbon nanotubes in combination with micro-sized short carbon fibers and graphite flakes as additional functional fillers for achieving this high multifunctionality. Here you see a blow-up of the multi-wall carbon nanotubes. They originally became delivered from the company. This was at that time biomaterial science, as kind of chunks of material, and only at very high magnifications you can see that these chunks of material consist of individual carbon nanotubes. And the challenge, of course, is to break up these chunks and to distribute the carbon nanotubes very uniformly in our material. And these are the short carbon fibers. You see they are about 7 micrometer in diameter. And this is a blow up of the graphite flakes. And all this is incorporated by a twin screw extrusion process. First, we make a master batch with this material. Then we thin it down with PPS only. And later, we add the short fibers and the graphite. Coming briefly to the properties, the tensile properties, also the tensile strength and the modulus, mainly increase with increasing content of carbon fibers the small amounts of multiple carbon nanotubes only gave us a little increase in the scatter here at each volume fraction, at each weight fraction of SCFs. And if we look at the volume electrical conductivity, then these multiple carbon nanotubes have a very drastic effect. So in this case, we need only a small amount of multiple carbon nanotubes to get over the threshold and to come to a higher electrical conductivity. With just carbon fibers only, we also get an increase, but at much higher weight fractions. And the values are on a saturation level somewhere here. But if we combine, for example, both, then we get a synergistic effect between the carbon nanotubes and the carbon fibers, so that we have more electrically conductive pathways to guide the electricity through the polymer. And this can also be further improved by the graphite flakes. We also looked at the tribological properties. This is 000, refers to only the PPS matrix, of which the specific wear rate is relatively high, in the range of 5 times 10 to the minus 5. When we add 3 weight% multiple carbon nanotubes, 10 weight% of graphite, and 10 weight% of short carbon fibers, we go down by several orders of magnitude here to 2 times 10 to the minus 7 cubic millimeter per Newton meter. Also, the friction coefficient is slightly improved by the combination of fillers. So in that case, if we prepare a spider diagram, then if we use only the matrix, you see that the properties are relatively low. These are the dotted blue curves. If we just use the multiple carbon nanotubes, we get, of course, a good improvement in the electrical conductivity, but not so much in the wear or in the tensile properties. If we use the carbon fibers only, this material is already reasonably well distributed in the properties, but the real multifunctionality we achieve when we have combinations of these, like multiple carbon nanotubes and short carbon fibers, or when we additional graphite, we get this pink curve, which is a very, very good envelope of this property profile which we wanted to achieve. Where can we use these materials? For example, as conductive bushings. These bushings can be found in a lot of joints of the automotives. For example, here the trunk has joints here and here. And if these automotives are electrocoated, then we must have some kind of conductivity here so that also every point in the car gets a uniform coating of the paint. But it's also used in plastic pump components of the mining industry, because it is important in many cases to avoid electrostatic discharge. So this can lead to explosions under the ground when the powdery atmosphere is around, but also in other applications like brake elements of high-speed cars, or this is an electrically conductive ball bearing, polymeric ball bearing, which are used in the food industry, for example. Byron mentioned already, we published a book on multifunctionality of polymer composites some time ago, back in 2015. And in fact, this book was recently translated into Chinese. It came out back in January of this year. The next application I would like to come to is the additive manufacturing of tribo-components. In our case, we use the fused filament fabrication method, where we have a printer extruder, a 3D printer extruder. From the nozzle here, molten polymer filament is placed, and when we can move the table up and down and forth and back, with this we can create any three-dimensional or print any three-dimensional structures we want. This is a machine we use. It's a homemade machine following the FFF principle. Here we have a spool on which the dry polymer foil filament is sitting, and then this filament is guided to a small extrusion unit in which it gets molten and finally extruded by this nozzle. The example here is a simple ball bearing, which we can print in this way. And we studied different materials. I only refer to polyamide 6 and polyamide 12 with carbon fibers, and another material from a company called Egus. They is a big producer of tribo products out of polymeric materials. And this material was called Iglidur J260. It's a thermoplastic polymer compound with additives and fillers. In both pictures you can see that the filaments themselves have a certain amount of voids, which hopefully can be closed during the melting process in order not to create or transfer these defects into the final structure. I will show you only one result, which is the diagram which I explained before, the depth wear rate against the PV product, the load collective. And only the best material in our case, of the various materials we tested here from different producers, was polyamide 12 with carbon fibers. And when we went to higher extrusion temperatures, then usually the material became better, so the initial slope and this curvature was flatter, and the values went to the left, to the right, so to higher PV values. But these materials, polyamide 6 and others lay in this range here, were not as good as the Iglidur material from Egus. Here we printed it in our laboratory. This was printed by EGOS with probably more commercial facility. And this material was also injection molded by EGOS. So you see, we get at least the same or better quality of the same material when we do the printing. In most cases, this is a bit the opposite, especially if the loading takes place by tensile loads. Then the voids create easier defects. But here the bearings, or during the pinion discus, the major load is a compressive load, so the voids don't play such an important role. EGOS prefers now selective laser sintering in most cases for their various parts. So this is a more precise and more accurate method, I think, than the fused filament fabrication method. Here we have our polymeric powder, and this is moved with a roller into another cavity, layer by layer, and after each layer, a laser beam is locally sintering the powder material. The rest of the material is removed and used later for other purposes. And so layer by layer, the part is built up here before it is completed. And the combination of electrical conductivity, or at least ESD shielding, is also done by EGOS company with SLS material, selective laser sintering material. So here's a powder material, and then the final component looks like this or this or this. Here we have electrostatic discharge. We have lubrication and maintenance-free components, high wear resistance, enhanced stiffness, usually due to the carbon nanotubes or whatever it is in there. We have a completely black material, and these powders are suitable for standard SLS systems. Also here we compared, we published a book in June 2020, my colleague Rolf Walter and myself, where we looked at the structural details like defects and the properties of additive manufactured polymer components. And this can be also bought by Elsevier company. The final part of my presentation will be on high temperature polymer coatings. Remember, I showed you this piston before. So there is a coating on the outside of the piston, on the piston skirt. But these coatings are also used in half shells, for example, for crankshafts in the engine of cars. And they can be composed of different materials. Since we have to do with high temperatures in these cases, we looked at two different materials, one from Solvay, polyamide imide powder called Torlon. The glass transition temperature is about 275 degrees C. And we use material from Performance Products, PBI, polybenzimidazole powder, which has even a much higher glass transition temperature of 423 degrees C. In these cases, you need a solvent in order to get these powders solved into a solution. And if we use this dimethylacetylene, DMAC, then this is very good for the PBI because the solution is stable up to 14 weeks compared to NMP as another solvent in which the solution is only stable for 3 days. And the production of the PBI solution is that the powder is placed in a high pressure reactor. And in addition, we put the solvent into it, and then at a high pressure of about 5 bars, and under heated condition, we can get 100% solution of the powder in this solvent. The temperature cycle is about from room temperature up to 230 degrees C, and then staying there for a while, about two hours or so, before we can cool it down. And then this solvent is used for making a very thin film on a particular substrate. It can be aluminum, or it can be steel, or it can be glass. And for this, we need an automatic film drawing device with a doctor blade with which we can adjust the height of the film and of the wet film, I would say. And then this substrate is moved, this slat is moved slowly to this direction, and then we get the coating on the surface. The final film thickness after curing is about 20 to 27 degrees, 25 micrometers. Here's a curing cycle for the PBE, but also for the PEI. So we first heated it up to 180 degrees C, then kept it there for a while, and then heated it up to a level between 215 degrees C to 280. Either this is the lowest temperature we needed for curing. This was the optimum temperature for the curing, also avoiding any warpage of the substrate if it's aluminum or some other lower melting material. It doesn't go forward. One moment. Okay. Here we go. Here also the specific wear rate was of special interest. And you see the material is better when this wear rate is lower. All in all, the polyamide imide coatings and the PBI coatings were in a reasonably good range between 10 to the minus 7 to 10 to the minus 6. But you see that the PBI was always superior for a given curing temperature condition than the polyamide imide. And this is for the highest curing temperature, and here we achieved the best value. If we look at the wear tracks, in this case, we use a so-called ring-on-plate wear testing machine where the ring rotates on a flat plate on which the coating is. Then the width of the wear track is a sign for the amount of wear. And here we see that in the PBI with 250 degrees C, the track is smaller than for the PAI at 250 degrees curing. Here we have a much wider wear track. This means a higher wear, which we have seen before. If we go to PBI at 280 degrees C, then this is a much lower magnification. Then the width of the wear track is only 248. Here it was 554. Also here I come to a result where we have the depth wear rate against the PV factor. If we look at the PBI only, the pure PBI coating or the bulk PBI, then we have this curve here. But if we put additional graphite or graphite and PTFE particle in it, then we can even reduce the slope, which is a specific wear rate, as well as the load-bearing capacity of this coating. And also the friction coefficient is improved by these internal lubricants. In the meantime, we use also a spray application process, not this other previous device which I showed. Here we can uniformly spray the coating onto a surface, either a larger plate or whatever, and with a uniform thickness in the micrometer range. And if we take such a plate, for example, and look what happens. Here in this case, the nozzle of the filament fabrication unit we use. And if we, for example, extrude ABS with this machine on a polyimide substrate, then you see it is very uniformly placed. This is the sliding direction to the left. But if we have a PBI substrate, then you see the polymer does not adhere to this substrate surface. This means we also can get anti-sticking behavior of PBI coatings. And this is a good sign, for example, when we would coat our nozzle with this PBI coating on the inside, so that, for example, it can be prevented the clogging of melt, especially of peak filaments in the die, prevents further processing. So if there is no adhesion between the nozzle and the polymer, the molten polymer, then we can get better and faster results. People have already used this in nozzles for cold spraying of solid hard particles onto metal surfaces. They call it cold spraying, but the temperature is 350 degrees C. The hard particles, usually if they use nozzles of ceramic or of steel, they find often a clogging of these hard particles so that the spray coating process is hindered. But if they use this bulk, high temperature PBI as a fully PBI nozzle, then this cold spraying works perfectly free. At this point, I would like to come to an end of my presentation. Before, I would like to mention some of our colleagues to acknowledge their contribution. Colleagues, for example, Dr. Chang Li from the University of Sydney. He worked with me on nanocomposites for tribology, Rolf Walter for the additive manufacturing, Eugen Padenko for the PBI coatings, and Dr. Noll for the electrical conductivity. We also acknowledge some funding agencies like the German Science Foundation, the German Ministry for Research and Technology, and also the Alexander von Humboldt Foundation, which funded postdocs to stay with us for 1 or 2 years. In addition, the industrial companies like Ticona, Superior Graphite, Egus, Ensinger, KS Gleitlager, which is a bearing manufacturer, Kolbe Schmidt, which is a manufacturer of these coatings on the pistons. Also, their help is highly esteemed. And to you, audience, I'd like to thank you very much for your attendance. And I'm now open for any questions.
Thank you, Professor Friedrich. We do have a few questions. The first question is, why do the nanoparticles increase the wear resistance? And they're wondering, does it improve the adhesion of the molecular structure? Does it act as a barrier? Does it reduce stiction? Your thoughts on that?
Yeah, there are various effects actually. I didn't point it out, it would be too much, but for example, they reduce the temperature in the contact region because even if they are ceramic particles, they are more thermally conductive than the polymer. So the thermal conductivity is improved, so the heat is more removed. Therefore, the frictional heat which we generate is reduced, so it doesn't soften the polymer itself. But on top of that, they also smoothen both the surface of the metallic counterpart and the transfer film, which is on there, and they smoothen the surface of the composite material. That means if you look at a worn surface, there are not so many visible cracks and defects, especially at the fiber matrix interface. They reduce the stress concentration there. And another effect, which is also evidenced by various of our tests, was that they can act as small rollers, or at least they can stay in the contact region and enhance the distance between the counterpart and the polymer composite surface, and therefore less interaction between any asperities of the steel surface with the polymer composite. So this is a combination. Also, many people say they stabilize the transfer film, so that the transfer film is not from time to time removed, but stays stable on the surface of the steel counterpart. Now, this is the things which we have observed, and also other people.
Thank you.
Well, pleasure.
To what extent can the tribological behavior of composites be simulated and predicted today?
That's a difficult task because the processes which take place during the wear experiment or during the wear of the real bearing or so or gear are very complex, and therefore one cannot simply take a relationship like wear rate is proportional to hardness. This is known for metals as a first rule of thumb to predict if the counterpart is harder, the wear rate is lower. But this is an empirical fact, partly. Also, some people have correlated the wear rate with the fracture toughness. This is always for abrasive wear the case, where you locally have some kind of crack formation in the surface, so the toughness of the material is also an important factor. But there are not so many attempts to really predict it with the real physical relationships. We have tried to predict it somehow by attributing to each part of the wear process, which, for example, is in a simple fiber matrix composite against the steel. First, thinning down of the polymer and then thinning down of the fibers. So the specific wear rate of the polymer itself and that of the fibers, and an interactive mechanism which happens when the fibers too much thin down. Then they start also to break and create broken pieces which are removed from the wall surface. So these are three major processes: matrix wear, fiber wear, and fiber interfacial removal. And if you can find the appropriate values for that, you can predict the wear rate of the composite quite reasonable. But you first must have these values. And therefore, for the pure fibers, you may do it in the experiment. For pure matrix, you can do it in the experiment. But for this fiber matrix cracking mechanism or fiber cracking and removal mechanism, this is a more difficult way. The other thing we have recently also carried out, we use artificial neural networks. That means we trained a network with a lot of experimental results. And then this network becomes more or less smart, and then it predicts the values which we did not use to feed this relationship, but it predicts the values quite well. So we have a training set of data, and we have a valuation set of data, and then this fits quite well, but you need a lot of data for that. So this is not real simulation. It helps to predict if you have enough results.
Thank you for that. There's indeed a lot of work to be done, and we appreciate you teaching us here today. We thank those that have attended today. We welcome you again on April 1st as we listen to Steve Arnold talk about practical developments in multi-scale modeling of composites. And with that, we bid you all good day.